Professor Pallas here with a lecture on the structure of lipids. Within the three macronutrient classes, there are carbohydrates, lipids, and proteins. Today we're going to discuss the second class, lipids. We're going to learn about the structure of these molecules. Lipids are hydrophobic. They are water-fearing molecules. In fact, they're not soluble in water, and they actually repel water. The word lipid comes from the base lipo, meaning fatty. And by definition, lipids are compounds that contain carbons, hydrogens, and oxygens, but they're noted to be insoluble in water. Think about it, carbohydrates all even have the same formula, C6H12O6, so they contain carbon, hydrogen, and oxygen, but those molecules are put together in a different way. That's what makes them carbohydrates. Lipids are structured differently, and they are noted to be insoluble in water. Lipids play a large role in helping maintain our overall sense of health and well-being. The key roles of lipids in the body are to store and provide energy. Lipids are also essential components of many compounds in the body. They insulate and protect our vital organs. In food, lipids help transport fat-soluble nutrients, and there's a whole category of vitamins that have to be carried around with fat. They're fat-soluble vitamins. Lipids also enhance the smell of food and the flavor of food. They promote a sense of satiety when we're eating, and they provide more calories per gram than the other two macronutrients. So this graphic should look familiar. We've seen this in other lectures. Carbohydrates and proteins contain 4 calories per gram. Fats contain 9 calories per gram. That's more than twice as much energy from fat than from carbohydrates or proteins. But remember, a healthy diet consists of all 3 of these macronutrients in the quantities specified in the AMDR. There are 3 main types of lipids, and the types of lipids, we look at them by their structure. That's their shape, their molecular shape. There are triglycerides, phospholipids, and sterols, and each of these perform different functions in the body. Triglycerides are composed of 3 fatty acids plus a glycerol. Phospholipids are composed of 2 fatty acid chains, a phosphate group, and a glycerol. And phospholipids are essential components of the membranes that surround every single cell in your body. So lipids are definitely important to health. Sterols are composed of 4 connecting rings of carbon and hydrogen. These do not provide energy, and the most commonly known sterol is cholesterol. So most lipids are composed of fatty acids. We talked about triglycerides having 3 and phospholipids having 2 fatty acids. So what's a fatty acid? A fatty acid is this long chain, this long carbohydrate chain that has hydrogens on it and some oxygen. So when we take a look at this long carbohydrate chain, this long chain, all these C's connected together, that's called the hydrocarbon chain. At one end of that chain, called the alpha end, there is an acid group called a carboxylic acid group. A carbon, 2 oxygens, and a hydrogen, COOH. That is the alpha end of the fatty acid chain. So when we talk about fatty acids, the length of the carbon chain matters. You can have short chains, medium chains, and long chain fatty acids. Short chain fatty acids have less than 8 carbons. Medium chains have 8 to 12 carbons, and long chains have more than 12 carbons. So the length of the chain matters. The shape and the saturation of the chain also matters. So when the carbons are connected with just single bonds, which is just denoted by a single line, C, single line C, it creates a straight shape. And this is considered a saturated molecule because it's only single bonds. When there's a double bond, which looks like C equals C, you can see that here on the slide, that's considered a double bond. When there's a double bond, there's a bend in the molecule. This is considered an unsaturated molecule. The level of saturation also matters. There can be more than one double bond in a molecule. When a molecule has just one double bond, it's considered a monounsaturated fatty acid, MUFA. When the molecule has two or more double bonds, it is considered a polyunsaturated fatty acid, a PUFA. So if we take a look here, we can see this molecule on the bottom of this slide, and you can see the saturated carbons on the left. So that carbon has 4 single lines coming out from it, but the carbon next to it has a double bond to an oxygen. That carbon is unsaturated because it has a double bond. So the structure and shape of the fatty acid influences its properties, what it can do. Longer chain fatty acids take longer to digest, longer to absorb, and longer to metabolize. The melting point is also affected by the structure of the fatty acids and specifically the bonds. Double bonds, unsaturated fatty acids, those molecules are bent. So they're bent and there's a bunch of them together, so they can't pack together really tight. And what happens is their melting point changes. So short chain, unsaturated molecules tend to be liquid at room temperature. Those are your oils. So they're not packed together tightly at all. They're liquid. Longer chain saturated molecules, so these are the ones that have all single bonds, these can pack together really tight, nice and neat, and they actually pack together so tightly that they form a solid. And these are your fats that are solid at room temperature. So this is butter, lard, coconut oil, and palm oil. So the structure of the fatty acid influences also the stability of the molecule and whether or not it's hydrogenated. So the stability is related to the location and the presence of a double bond. When we have a double bond, it's easily broken, and that double bond can be broken through a process called oxidation. When the double bond is oxidized, it alters the chemical structure of the fat, and the fat actually goes bad, and it develops a state that we call rancid. And if you've ever smelled a rancid fat, it's a very distinct smell. So that rancidity of fat is related to that double bond being broken by the presence of oxygen. Hydrogenation or hydrogenation, there are 2 different ways you could pronounce that. It depends on whether you're a chemist or a nutritionist or a dietitian, is when we add hydrogen to an unsaturated fatty acid to make it more saturated and more solid at room temperature. Why would we do that? Because it reduces the rate at which the product will go rancid. So when we add hydrogen to something, when we hydrogenate an oil, we increase its shelf stability. If you're a food manufacturer, that's a really valuable thing to be able to do. So if we take a look at this molecule, again here on the bottom, we see the saturated carbon has 4 single bonds. The unsaturated molecule has that double bond, which has danger of being broken. It can be oxidized, and then the fat goes bad and rancid. There are 3 common fatty acids that are found in food: saturated, monounsaturated, and polyunsaturated. Saturated fatty acid foods contain only single bonds and they pack together nice and neat, really tightly. They're solid at room temperature. So these are foods like butter, lard, coconut oil, and palm oil. They're solid at room temperature. A monounsaturated fatty acid has only one double bond. So this is things like olive oil, peanut oil, olives, and avocados. Monounsaturated fatty acids are also called MUFAs. These are good beneficial parts of your diet. Your polyunsaturated fatty acids, or PUFAs, contain two or more double bonds. These are also beneficial products to include in your diet. PUFAs are high in fatty fish, soy milk, corn oil, and safflower oil. So that is an introduction to the structure of lipids. I would encourage you to reread this section of your textbook. And if you have any questions, any concerns, or if you'd like to talk more about this topic, please reach out to me. I'm happy to schedule a Zoom meeting with you or a FaceTime with you or a traditional phone call, whatever works best. Thank you for your time.